experiment is just some experiment. So if we sit here and normally, I think at the start of the year we did the M&Ms, and we did that. That was an experiment. I'm not going to do it again. My wife's been mad at me for spending too much money, so I'm not buying you guys M&Ms again. Sorry. But that was a probability experiment where you do something and try to see what's going to occur. And I think when we did the probability experiment, and I could be wrong because it seemed like this year came out a little different than it did in past years, because in past years, blue was always like a predominant color. And I think this year, what was it? Didn't we have more of something else? It was like red or something. And it wasn't, and I probably told you this too, it wasn't 15 years ago or so, you guys were probably real small, wouldn't have a clue. They didn't have red M&Ms because the red dye supposedly caused cancer. All right, so you know it was probably old wives' tale, but everybody believed it, so they wouldn't eat the red M&Ms. So people quit buying M&Ms, and so M&M took out the red, but then they put them back in. They got some kind of new dye. An outcome is a result of a single trial. So if you drew out one M&M, figuring out the color, that's an outcome. If you flip the coin and you got head or tail, that's an outcome. Sample space is the set of all possible outcomes. This is real important with sample space. You've got to be able to, and it takes a while sometimes, but anytime I'm doing any kind of probability problem, I list out the sample space, even if it's like rolling 2 die, all right? So when we come to a test or a quiz or anything, and I say, okay, you're going to roll 2 die and figure out what the probability is of getting this, I do this every time. You could get a 1-1, you could get a 1-2, you could get a 1-3, you could get a 1-4, you could get a 1-5, you could get a 1-6, so on, so on, so on. You list them all out. Even though it takes a little while, it's better to take a minute or two and write them all out, your whole sample space, than to screw up the whole problem. So that's a set of all possible outcomes. A tree diagram that we talked about last time will give you all the possible outcomes. An event consists of one or more outcomes and is a subset of the sample space. So an event could be you wanted to roll a 1 and a 2. So that might be your event, the event that you're looking for. When we do probabilities, probability is always written this way: capital P, parentheses, and then inside the parentheses is whatever event you want to occur. So this is the probability of whatever you want to occur. Maybe if we were rolling the dice, you'd want a probability that you got a 1-2. Or if you were totaling them up for some reason, maybe you want the probability that you got a total of 3. 1 plus 2 is 3. So that's an event. Tree diagram. This is a tree diagram here. I listed first choice, soda or juice. Second choice, bagel, rye bread, white bread. So there's 3 branches coming off the soda because you could choose either one of those. There's 3 branches coming off the juice because you could choose either one of those. And then your third choice, cheese, pastrami, roast beef, turkey. You got 4 choices out here for apparently your kind of sandwich that you're getting. And then out here, this whole thing here is your sample space. Each one of these is a different event. So if we made a tree diagram for that, we could figure out pretty quickly. And there's a lot of times where I won't ask you to make the whole tree diagram because this is big and long and drawn out. But if you make the first couple parts of this, like maybe you make those first couple parts right there, you can tell there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 different outcomes here. Well, if we go on down, there's going to be 8 here, there's going to be 8 there, so there's a total of 24 possible outcomes. And then if you're trying to find the probability, if you want the probability that you do soda bagel with cheese. Well, how many different times is soda, bagel, and cheese listed out of this list? 1. So our probability would be 1 out of 24. We're just adding to the notes, Michael, that we started a month ago or so. So that would be our probability, 1 out of 24. Please, when you're doing probabilities, don't write stuff like this. No slashes. We want a fraction bar. Otherwise, you're going to get confused. That's the same tree diagram. We want the probability that we get soda, white, and a turkey. We know that there's 24 total outcomes, so that goes on bottom. And then we look for soda, white, turkey. We don't even really have to look for it. How many times are you going to choose soda, white, and turkey? There's only one of those, right? It's not going to be listed 2 or 3 times down through here. So there's 1. Now, if we got rid of part of it, if we said we wanted to know the probability that somebody picked soda and white bread, and we didn't care about the meat or the cheese or whatever they put on the sandwich, we just wanted soda and white bread, then we would come down here and we would look right here at how many possible how many favorable outcomes are there. So it'd be 4 out of 24. And we can reduce that down. 4 will go into 4 once, 4 will go into 24 6 times. So if we were walking around this store being some kind of weird person looking at people who picked the soda and white bread for whatever reason, about 1 out of every 6 people would probably pick something like that. Probability experiments, again, if we roll a die and we want an outcome to be 3, your sample space, 1, 2, 3, 4, 5, or 6. Maybe you want the die to be, or you want the find the probability that the die comes up even, 2, 4, 6. All different kinds of things that could happen there, but just know a die, deck of cards. We talked a little bit about that last time. Identifying sample space. A probability experiment consists of tossing a coin and then rolling a 6-sided die. So we're going to make a tree diagram so that we can see this. And again, you don't always have to make a tree diagram. It's just one of the ways that makes it sort of easy to make sure you don't miss anything. The one thing, if you are doing a sample space, you don't want to just start listing. If I say, if we roll 2 die, what's the possible outcomes? And you go, well, you could get a 5 and a 6. You could get a 2 and a 3. If you start just listing things at random, are you ever going to find them all? You're probably going to mess up and miss some. So you want to go in some kind of order. Previous. We make this tree diagram for that problem. Now I got to remember what it was. So we want probability that you're tossing a coin and then you roll a 6-sided die. I'll just use the picture. I was going to make mine. So we could get a head. Well, if we get a head on the coin, then we should have 6 branches coming off of that. Because we could get a head, then we roll the die, we could get a 1. We could get a head, then a 2, head, then a 3, head, then a 4, so on, so on. And down here is starting of the list of your sample space, all the possible outcomes. If we roll a tail, or if we flip a tail, we could get a 1, a 2, a 3, 4, 5, or a 6. So that right there is your whole sample space. That one's not too difficult. 12 possible outcomes. So if I said, what's the probability of getting a tail 5? For whatever reason, we want to flip a tail and get a 5. How many times does T5 show up in our sample space? 1. So it's 1 out of how many total? 12. So it would be 1/12. A lot of times in this book, they change it into a percentage. Somebody grab their calculator out for me real quick and Help me out. What's 1/12 is a percent or is a decimal? So sometimes we'll give the answer as a fraction. Sometimes we'll give the answer as a decimal. Sometimes we'll change that decimal into a percentage by bumping it over 2 places and give a percent. Depends on the problem. Depends what you're dealing with, right? Or who you're talking to. If you're talking to me, I'd rather see it 1 out of 12. That makes more sense to me. Maybe if I'm talking to Miss Clark, she likes percents better. I'm saying, and I tell her 8% of the time you're going to get a tail than a 5. Maybe that makes more sense. All right? Depends on the problem and on what you're using it for. Simple event. You guys say this is about where we left off. An event that consists of a single outcome. So we just want, you got to be careful because it says one outcome. It doesn't just mean a head. It means one outcome for the whole experiment, whatever we're doing. So we flipped a coin, we rolled the die. So H3 is a simple event. T5, like we just had on the last one, that's a simple event. An event that consists of more than one outcome is not a simple event. That's sort of common sense, right? And we're going to talk about those events later on in this chapter. If you, let's say you wanted to, maybe you wanted to find the probability that you were doing this, these actions 2 or 3 times. You wanted to get a head 3, and then you wanted to get a tail 5. Then that's not a simple event because now we've stuck in more than one thing. Determine whether the event is simple or not. You roll a 6-sided die. Event B is rolling at least a 4. Is that going to be simple? If it's at least a 4, what's that mean it could be? It could be 4 or 5 or 6. Is that going to be a simple event? No, because there's more than one possible thing that could occur. So it's not simple. Fundamental counting principle. This is very, very important. This is about where we got to. Fundamental counting principle. If one event can occur M times, second event can occur N ways, third event can occur R ways. I'm not sure why my R is not red like the M and the N, but then instead of making this big long tree diagram or trying to find the possible outcomes, our sample space, by listing it all out, we could find the total outcomes just by doing this. This is going to equal your total possible outcomes. You just take how many items there are in M times how many items in N times how many items in R. So if I tell you in my closet this morning when I got up and I started to get ready for school, I have 15 pairs of pants, 22 shirts, and 43 ties. You guys better enjoy this because I actually counted this stuff this morning just for this. So I have that, and I want to know how many different outfits I could have wore this morning. And I know Camden's sitting over here going, why'd you pick that one? That's a real good outfit. I don't need your fashion knowledge here, Camden. So quit messing with me about my dress. So we got 15 pairs of pants, 22 shirts. I really don't want to make a tree diagram and say, okay, I got a Oxford. I'm not even sure what kind of shirt Oxford is, but an Oxford blue shirt, Oxford tan shirt, an Oxford, so on and so on. I don't want to list all those. That's just too much. Because you're going to have 15 in the first list, and then branching off of each one of those. I'm sorry, I put shirts first. You're going to have 22 branches coming off each one. That's way too much. So all we have to do to find the total possible outcomes, how many different pairs of pants do I have to pick from? 15. So I can do 15 times how many shirts? 22 times how many ties? Somebody multiply that for me.
14,000.
So how many different outfits could I put together out of my closet there at the house? 14,190. What's the probability that I got up this morning and I picked the outfit that I have on?
One out of that.
One out of that. Alright? Because there's only one way I could have put this outfit together. Pick this certain pair of pants, this shirt, this top. Can be extended for any number of events occurring in sequence. So it doesn't just have to stop at 3. It could be 4, 5, 6, 7, 8, 9, however many events you have going on. And notice, this isn't, what we do in here won't be stuff like if you've dealt with probability in the past. We won't be dealing a whole lot with probabilities like 1 out of 6. All right? We're going to be dealing with probabilities like 1 out of 14,190. So we're going to be dealing with a lot bigger numbers. Example, you're purchasing a new car. The possible manufacturer's car sizes and colors are listed below. So we're going out to buy a new car. How many choices do we have for the manufacturer? How many choices for the car size? 2, because your folks aren't buying you some big Cadillac car that's 20 feet long. Color. How many choices for color? 4. How many different possible outcomes are there? All we're going to do, take those 3 numbers, multiply them together. 24. There's 24 different cars you could pick. What's the probability that you pick a Ford, mid-size, white? 1 out of 24. So that's what they did there. Used a fundamental counting principle again. They made a tree diagram for it here. If we don't have to do that, sometimes we may have to, but if we don't have to, we'd rather not do all that extra work. Pizza place offers 3 kinds of crust. Can't see what that says. 12 toppings. And 3 kinds of cheeses. How many different 1-topping pizzas could they make? So if we do this, what's your first choice? How many different kinds of crust could you pick? So 3 times, if we're just picking 1 topping, how many different toppings could we pick? 12 times 3. What's that give us? Seems a little hot. Oh no, that is right. 108. So that's for 1 topping. How's that going to change if we want to pick 2 toppings?
Cut it in half, would it?
Huh?
We'll cut it in half, would it?
I don't know, will it?
Or
How many different crusts do we still have to pick from?
24.
We pick our first topping. How many choices do we have for the first topping? So that's still the same. Now we gotta pick a second topping this time. So now you only have 11 to choose from, because we're picking 2 toppings, not just double pepperoni or something like that. So it's 3 times 12 times 11. We still gotta pick our what? So now you're just throwing in another part to that. What's that get us?
1,188.
So when we look at this, you go to Pizza Hut tonight. We just said a 2-topping pizza. They serve 3, 4, 5 toppings, 6 toppings, you know, however many toppings you want. How many different pizzas do you think Pizza Hut can actually make? A bunch, right? All right, types of probability. There's 3 different types of probability. The first one, classical or theoretical probability. Each outcome in a sample space is equally likely. This is the one that we normally deal with. Remember, when you're doing probability, it's always going to be probability of an event equals favorable on top, what outcome you want to happen, over total possible outcomes on bottom. Favorable outcomes on top, total possible outcomes on bottom. Favorable, and you may have had teachers in the past that said on top was wins, something like that, what you want to occur. We're not going to say wins because that gets confused with odds, which we'll get to here in just a minute. Stupid, did he? Starting to get worried now. I felt bad about making fun of him when he said he's going to kill himself.
When did he say that? Yes.
I'd really feel bad if something happened. We already talked about this. Probabilities can be written as fractions, decimals, or percents. This book, a lot of times, writes them as decimals. I like to write them as fractions. When you get out into the real world, a lot of times they're written as percentages. All right? When you see, if you watch ESPN, now they're all big on giving probabilities. What's the probability that Miami was going to beat Baltimore last night? And they always give Miami's got a 20% chance of winning, or every game they're doing that now. How come you think they give percentages and not fractions or decimals?
Easier to reason. Everybody would that would.
It makes more sense to a normal person. So that's why they do it that way. Then how come, if that's the case, I go to the racetrack a lot and I bet on horses all the time, so I'm always broke. I go to the racetrack, should probably stop the recording here. I go to the racetrack and I bet on these horses. They don't ever give anything in percents. How come they always give stuff as fractions and odds and using a colon? How come they do it different ways?
So you don't want money?
Exactly. They want to confuse you. They want you to be confused. They don't want you to understand everything. They want you to be confused so that they get your money. ESPN's not making any money off this, so they don't care if you're confused or not. They'd rather you understand what's going on. Finding classical probability, you roll a six-sided die, find the probability of each event. Event A, so we want to find the probability of rolling a 3. 1 out of 6. Some of these are pretty easy. We could change that to a decimal, we could change it to a percent. For something like this, 1 out of 6, I think that's the best form because now Sydney knows that if she rolls the dice 6 times, she can expect to get how many 3s? 1 out of those 6 rolls. Event B, rolling a 7. What's the probability of rolling a 7? 0. And with classical probability, with any probability, I can't remember if this is on this PowerPoint or not. I think it is somewhere, but I'll write it down up here anyway. Probability has to always be greater than or equal to 0 and less than or equal to 1. So whenever you have a probability, it's got to be from 0 to 1. The lowest it can be is 0. What's the probability of 0 tell you? The event's what? Can occur. Event can't happen. It can't happen. What's the probability of 1 tell you? It's always going to happen. So if I say, what's the probability of picking a smart person, smart student in my Brown 1 class? What's the probability? 1. Thank you. So probability would be 1, picking a smart person out of here, right? I hope you guys think that way. Event C, rolling a number less than 5. So we want a number less than 5. How many numbers are less than 5? 4. Yeah, 4, 3, 2, 1. So 4 out of 6, and we probably want to reduce that. 4 out of 6 reduces to 2 out of 3. On the big calculators, I'll borrow your calculator for a second. On the big calculators, if you have a fraction and you're not sure how to reduce it, you can always do this. If you do parentheses 2 divided by, 4 divided by 6. So parentheses 4 divided by 6, close the parenthesis. If you go to math, the first button says fraction. You put in fraction and it says fraction right there on your calculator. You hit equals again and it will reduce it for you. Now I'm hoping that something like this you can reduce yourself, right? But when we get something like 524 over 1,000, and you have to reduce that, and you're going, I don't know how to reduce that. Then you take your calculator and you do parentheses, 524 divided by 1,000, close the parentheses, hit math, fraction, hit enter, and it'll tell you it reduces down to 131 over 250. With some of the bigger numbers, that might be a good thing, so you can reduce them down, get something that looks a little better. Just did all that. Notice these just came right out of the book and they changed every one of them into a decimal instead of leaving them as a fraction. If there's small things like that, I wouldn't change any of them to a decimal. I'd leave everything as a fraction. Empirical probability. Empirical probability is based on observations that you get from the experiments. So this would be like when we did the M&Ms. When we said, okay, we buy another bag of M&Ms, we're probably going to get more red M&Ms than anything else. That's using empirical probability. We're basing that off of what we see. Now notice this is off of experiments. It's when we actually do something to try to get these outcomes to happen. A lot of stuff like insurance is based off of probabilities, but they don't do experiments so much to get it. They look at past occurrences. Can't go out and pick a driver that's 16 years old, one that's 17, one that's 18, one that's 19, and just say, okay, just keep driving until you wreck, and we'll see who wrecks first, and we'll make their insurance higher. We can't do it that way. Relative frequency of an event. Relative frequency is just how often it occurs. Same setup here. When you do an empirical probability, it looks different. It's sort of worded different, but it's just worded different because you're actually looking at your overall experiment. So this would be, when we were doing the M&Ms, this would be like, how many red M&Ms did we get? So what frequency did the red show up over the total frequency or the total M&Ms, how many total M&Ms we had. So it looks a little different, but it's basically the same thing. Favorable over total. F stands for frequency. Hopefully you haven't forgotten that. N, just like before, N is for your total in that certain sample space that you're dealing with. A company is conducting an online survey of randomly selected individuals to determine if traffic congestion is a problem in their community. So far, 320 people have responded to the survey. What is the probability the next person that responds to the survey says that traffic congestion is a serious problem in their community? So we're looking at this. Again, it's going to be what we want over the total. Well, what are they saying that we want? What's the probability that the next person who responds says that it's a serious problem? So how many people have said it's a serious problem? 123. Out of, they gave it to you here, what would we have to do with this if they didn't give us this bottom number? Add them all up to find that. Now this is why the book changes theirs into decimal, because if I tell you 123 out of 320 is the probability, does that really make any sense to you? Doesn't really mean anything, right? So if we change it to a decimal, somebody help me out, what is that as a decimal? 0.38. And then I would even change it to a percent. What is it as a percent then? 38%. So there's a 38% chance that the next person that we talk to or next person that responds is gonna say it's a serious problem. And either one of these make a little more sense this time than the fraction. Because if you say, yeah, there's a 123 out of 320 chance, that's not gonna mean anything to anybody. The numbers are getting too big. Law of large numbers. All the law of large numbers says, and sort of simplify this down a little bit as you write it, you can sort of figure out what you need and what you don't need. If I got a coin here, I got a penny, and I sit here and I flip it. If I flip it 10 times, I should get how many heads and how many tails? You should get the same amount, right? Because the coins should have the same. Is that going to occur? No. If I gave each one of you a penny and we each flipped it 10 times, I'll guarantee that not everybody gets 5 and 5. It's not going to happen that way. What the law of large numbers says is if we do it 10 times, yeah, we're probably not going to get 5 and 5. If we do it 100 times, we should get 50 and 50. We're probably still not going to get that. Not everybody's going to get 50 and 50. But the larger we get with how many times we do it, when we get up to doing it 1,000,000 times, so I have each one of you flip the coin 1,000,000 times, we're going to get closer and closer and closer to actually being at the probability that should occur. 1/2 of the time. So that's all the law of large numbers says. And you notice that's what they've done here. What's that say? Proportion that are heads. So they figured out heads. Well, they flipped it, looks like 10 times down here. Looks like they got like 8 heads. Then they flipped it a few more times, and they end up getting more tails. Then all of a sudden, it started leveling off here, and it stayed about here. And how many heads did they start to get? Looked like they got closer and closer to getting about 50% of the time. 5 heads, 5 tails if we did it 10, so on and so on. So, law of large numbers just says the more times you do it, the better chance you're going to have of getting closer to what the classical probability is. So when you see stuff on the news and they talk about, oh yeah, there's a 30% chance of rain, that's a probability, right? 30% chance of rain, what are they basing that off of? Past similar days. Past days where the barometric pressure was this, and this number was this, and this number was this. And they say, okay, 30% of those days it rained. 70% of those days it didn't rain. So whenever you're watching the news, it always bothers me because everybody says, oh, stupid weather forecasters are always wrong. No, they're not. They're always right. Because if they said there's a 30% chance of rain tonight for the football game, well, then everybody's going to bring their umbrellas, right? And then it's not going to rain, and people are going to be mad that it didn't rain. Well, what'd they tell you? There was a 70% chance that it wasn't going to rain. Best weather forecast is when they say this: 50% chance of rain. As soon as they say there's a 50% chance of rain, everybody thinks it's going to do what? Rain, for sure. It's most definitely going to rain. Well, if there's a 50% chance of rain, then there's also a 50% chance it's not going to rain. That's like the weather forecaster deciding, you know what, I didn't really feel like coming to work today, so I'm just going to say, it's 50-50. It could go either way. All right? Where did they base these off of? Past things. And that's what this is. As we go, 1,000 years from now, should there be anything like this? If we continue, if the earth doesn't just go back to the Stone Age because somebody does something stupid and shoots off a bunch of nuclear weapons or something, if we continue on the path that we're on, should we be able to predict the weather almost to a T? Yeah, because we'll have more data to base everything off of, right? There's probably not any data about the barometric pressure and all that stuff from back in 2000 AD. Those records weren't kept. Now we have those records and we're keeping them, so 1,000 years from now we'll probably be able to predict exactly what the weather is going to be like each day. Subjective probability. Subjective probability is intuition, estimates. And notice educated guess is there is in red because that's a stupid phrase. There's no such thing as an educated guess. If you're educated, you don't need to guess. You make a prediction of what's going to happen based on your knowledge. Doctors do this a lot. Camden goes to the doctor to have his knee looked at, and the doctor says, yeah, you got a broken shoulder. Well, probably a pretty good chance he needs to get a different doctor, right? Because he's not doing stuff right. Doctors look at things, and you ever wonder why, if you're sitting in the room, you're sitting in the little room here on the doctor's table, and the doctor comes in and he looks at you and he says, okay, what's wrong with you? And then all of a sudden he leaves for 15 minutes. And he's like, come on, I want to get out of here. What's he doing or she doing at that point? You gave him your symptoms, or you gave them your symptoms, and now they go look up stuff. They're going to try to match something to it. All right? And they come back and they say, well, we think there's a pretty good chance, there's about a 40% chance that maybe this is what's going on. Hopefully they know better than 40% chance. People always like this. Doctor tells you you got a 90% chance of living after this surgery. Now, the part they don't think about is, and that means what? You got a 10% chance of not making it through the surgery. Classified statement is classical, empirical, subjective. Probability that you will be married at age 30 is 0.50. Classical, empirical, or subjective? What do you think they did there? Make a guess. Empirical, maybe?
Yeah.
Do we know for sure when people are going to get married? No, so we're basing it off of what we think might occur, what's occurred in the past, maybe a little bit. Probability that a voter chosen at random will vote Republican. Empirical. Based on some kind of survey or some kind, you surveyed everybody as they were walking through the door. Probability of winning a 1,000 ticket raffle with one ticket is 1 out of 1,000. That's classical. Classical's pretty easy to pick out because it's just straightforward. You got this chance out of this total outcomes. Range of probabilities, we talked about this earlier, I guess it was on this PowerPoint. Probability of an event's always going to be between from 0 to 1. If it's 0, the event never occurs. If it's 1, it always occurs. If the probability comes out to be 0.05 or 5% or less, that's an unusual event. So if the event doesn't happen more than 5% of the time, then it's an unusual event. And all probabilities in a sample space always got to add to 1. Whenever you're doing some kind of experiment or whatever it is, the probabilities always have to add up to 1 whole. Can't add up to more than that, they can't add up to less than that. They always got to add up to 1 exactly. Now ours, if we were to do a bunch of probabilities for, let's say, the M&Ms, and we said, okay, probability of getting a red M&M was 38.38 or 38%. Probability of getting a blue M&M was 10.10. Probability of getting a green M&M was 24. Probability of getting a yellow M&M was 26. And we go to add them all up, and they don't add up quite to 1 whole. That just means we probably rounded somewhere a little wrong. So we should be somewhere close to 1. So if you're like 0.99 or if you're at 1.01, something like that, you're probably okay. But they should add up to 1 whole. With this, if you have, again, impossible to happen is at 0, unlikely to happen is less than 50%, likely to happen is more than 50%, certain to happen or always going to happen is at 1. Complement of an event. Let's just use a die again. What's our sample space if we roll a die?
1, 2, 3, 4, 5, 6.
That's our sample space. We're rolling a die. I want, the events I want to happen is I want to get a 1 or a 5. So this is our event. That's what we want to occur. When you're doing the complement of it, the complement is everything out of the sample space other than those. So the complement of that event would just be 2, 3, 4, and 6. So the complement is everything else. So you got the event, then you got everything else. That's the complement. That's all a complement is. When we show a complement here, this is our event. All this stuff out here is the complement. When we show that we want to complement, we use this little apostrophe sort of at the top. So that means we want everything other than that event. So just remember that that means that you want the other stuff, the complement of whatever it is that you're looking to do. So are you feeling better?
Yeah, my throat still kind of hurts.
You look a little flush. This is called E prime. That little symbol's E prime. So you'll hear me say E prime. Whenever you're doing these events, the complement of an event and the event, their probabilities should total up to one whole. So if I told you the probability of the event that I want to occur was 0.32, and I say find the probability of the complement, what would you do there to find that probability of the complement? Take that and subtract it from one whole. So you get like 0.68. So those two always have to add up to one whole together. The event, the probability that the event occurs, the probability that the complement occurs. Probably should erase this so you can see this. So that's what we were just saying. So 1 minus the complement would give you the event. 1 minus the event would give you the complement. All these are saying the same thing, just written in different forms. Use survey a sample of 1,000 employees at a company and report the age of each. Find the probability of randomly choosing an employee who is not between 25 and 34 years old. So let's do this. Let's find the probability that the person is between 25 and 34. How many people are between 25 and 34? So that's 366 out of 1,000. We want the people who are not, so we're doing the probability of the complement. That's what we actually want. All we really have to do here is, should add up to one whole here, so we could change that to a decimal. What is that as a decimal? 0.366. And we're going to take that and we're going to subtract it from one whole. What's that leave us with?
0.63.
So the probability that we're looking for, about 63% of the time, we'll pick somebody who's not between those two ages. So they did that, same thing we just did. Then they did that. Now, could we have found it by adding these up and then putting that over 1,000? Yeah, might have taken just a little bit longer. Probability experiment consists of tossing a coin and spinning the spinner shown. The spinner is equally likely to land on each number. Sorry, Malachi, I didn't hear you. It's nice of you to be polite and not real loud. Spinner is equally likely to land on each number. Use a tree diagram to find the probability of tossing a tail and spinning an odd number. So if we wanted to use a tree diagram on this, we're going to do something like this. We could get a head, we could get a tail. How many possible outcomes we got on our thing there? 8. So how many branches am I going to have coming off the heads? 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I hate making tree diagrams. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. What's our first possible outcome here? Could get a head and a what? Head and a 1, head 2, head 3. For this one, do you really need the tree diagram? You could probably figure this sample space out just by writing it out, right? Head 4, Ed 5, Ed 6, tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. And we want, find the probability of tossing a tail and spinning an odd number. So we want a tail and an odd number. How many total possible outcomes do we have? 12. We want a tail and an odd number. Is this one a favorable one? This one? What I do is I usually go through the sample space once I make it, and I circle the ones that are favorable.
Why didn't you do the 7 and
Oops. Because I was thinking of a die instead of a spin. So how many, so there's not 12, 16, thank you. How many favorable outcomes are there? If we wanted to change that to a decimal, what's it going to be as a decimal? 4 out of 16. Come on, you don't need a calculator for that. What percent is that? 25%. They made the tree diagram, did all that stuff. 25%. Probability of using fundamental accounting principle. Your college identification number consists of 8 digits. Each digit can be 0 through 9. And each digit can be repeated. So that means you could have all zeros or all nines, or you could have a 0, 0, 1, 1, so on and so on. What's the probability of getting your college identification number when randomly generating 8 digits? Do I really want to go through and write 0, 1, 2, 3, all the way to 9 and put 9 branches off each one of those?
No.
Because I'm going to have to do that 8 times. And that's going to be way too much. So using the fundamental counting principle, we got 8 different things. I usually make little blanks for myself. 1, 2, 3, 4, 5, 6, 7, 8. How many different numbers can I get for this first number? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Be careful when you do that, all right? Because a lot of people think 9, and there's actually 10. How many different numbers could you get when you pick the second number? 10, because it says it can be repeated, right? If it says you can't repeat any of the numbers, then that would be 9. How many for the third number? 10, fourth number, fifth. What are we going to do with all those? Times. Somebody multiply all those together for me. What could you do on your calculator to make it easier? So use 10, and then you have this little button, little caret button. You want 10 to the, what power are you going to take it to? 8th power. 10 to the 8th power. What's it tell you?
9?
Probably starts with a 1, right? How many zeros? 8. So what is that number?
100 million.
100 million. So how many different students could one college have? They could have 100 million students. And everybody still have their own identification number. So you got your ID. Next year you go and you got your ID. What's the probability that you got that ID? 1 out of what? 100 million. 1 out of 100 million. So you can go home and tell your folks how special you are that you got that ID number. You're not just 1 in a million, you're 1 out of 100 million. You're even more special than that. Odds. Important here, odds. Odds are a little different. I like teaching odds because it teaches you how to gamble. So you go to the track and lose all your money.
How often do you gamble?
Yeah, just about every day. Call the bookie every day.
You do what?
Call the bookie. Bookie. That's good. That's good that Malachi doesn't know what a bookie is. That means mom's kept you sheltered a little bit. You don't have to.
Don't worry. What is it?
A bookie's a person who takes bets. So if you're like betting on a football game or something, called them this morning and bet on you guys.
Who do you call?
I'm not going to tell you that. If I start giving my bookie's name out, he gets mad at me. He won't take my bets no more.
Is it the same person every week?
Yeah. It's illegal to do stuff like that. You can't be telling on people that they won't.
It could be anybody. It could be anybody.
You guys laugh, but the people I ran around with, that was a big deal when I was growing up.
What?
They had bookies. Had a couple guys out of Indianapolis and stuff that they called all the time. And they were always losing money. And then they'd win one thing. Oh, I won $200 yesterday. Yeah, but you lost like $1,500 last week.
Doing good. How
Yeah.
much do you bet?
I don't bet anything.
You just.
My brothers even, when we went out to Las Vegas, my brothers even made fun of me.
But you didn't do it?
Because I didn't, because I wouldn't, we'd be sitting at a blackjack table and I'd be betting like $1. And they were betting like 20 or 50 or something. And I'm like, I'm not betting 20, $1.
Like, I know my luck. I wouldn't do that.
And every time I put down that $1, that dealer would go, really? Yep.
Really?
Unless you're gonna let me bet 50 cents, then I'll change.
If you're a college video, like you get a lot of money out of that.
You don't get a lot of money. You're just a worker. It's the casino's money. Odds of winning. When you're dealing with odds, instead of favorable compared to total, a lot of times odds are written with a colon, and it's wins compared to losses. Now I actually gave you two different ways here, because it could be wins compared to losses, or it could be losses compared to wins. Sometimes they switch them around on you. And again, why do they switch them around on you? Confuse you. Just to try to confuse you. So if the Kentucky Derby, whenever the Kentucky Derby or the Preakness or any of those big races that you see on TV, those big horse races, they when they show you a horse's odds, and it's something like 1 to 3, that means they're going to win once and lose 3 times. So if they ran 4 races, you would expect that they won once and lost 3. All right? So when they show you something like this, a horse has 3 to 2 odds. That means they're going to win 3 times and lose twice. All right? Out of a total of 5 races. So if we want the probability that this horse is going to win, for this one right here, you take this number, that goes on top, and then your bottom number, you have to add these together. So that means it's going to be about 60%. 60% chance that they're going to win. Now that also goes with the betting, because if they're saying this, and I probably shouldn't even tell you this because this will probably get me in trouble. If you were going to bet on this horse, if you bet $1, guess how much you win? $3. This horse, if you bet $3, guess how much you win? $2. All right? So with this horse, you're putting up chance to lose $3 and only gaining back $2. Doesn't make a whole lot of sense, right? But that means that horse is a heavy, heavy favorite. That they're probably, there's a very, very good chance that they're going to win that race. One of the, what did I just hear on the radio? Must have been something about the World Series or something. But it was just on the radio a couple days ago, and it was, if you went to Vegas, man, I can't remember what it was. If you went to Vegas and you made a bet, you could put up $40,000 to win $100. It was something ridiculous. All right. So you put up 40,000, take a chance of losing that 40,000 to make $100. Dumb as could be. You know, why you would ever place a bet like that? It's just ignorance. The assignment's the same assignment you've had for the last month.
Still one question. Wait, what?
You've had this like 3 or 4 different times now. Well, maybe this, I don't know. Maybe the sub didn't, yeah, we had it. Or no, maybe.
I already got it written in mine.
I'm pretty sure we had it once, and then the sub was supposed to give it to you again, and I don't know. If not, write it down. That's your assignment.
Oh, I was